Hey, this is Math 7, Unit 8, Lesson 4, Estimating Probabilities Through Repeated Experiments. So we're going to do some experimenting today. So first of all, we warm up with decimals on the number line just to have a feeling of where things are. Now again, these are here, they're using these numbers. Why? Because if something has no chance of happening, it has a probability of 0. If it's certain going to happen, it has a probability of 1. So this is something that is certain, and this is something that is never going to happen, and we would call it impossible over here. So the reason we're doing this activity, see where do these decimals go, is just so you can remember kind of the order of things. So the higher a decimal value is, the more certain it is in terms of a probability for later on. So that's why we're doing this here today, in case you're wondering, why are we playing with decimals today? So let's place these on the number line. We'll do the first one first, 0.5, which is halfway through. So we can put that here in the middle as 0.5. That's easy enough. 0.75 is halfway between 0.5 and 1. So that's easy to place there between those ones. I'm going to jump down here and do the 0.25, which is between 0 and 0.5. And then we have the 0.33 and the 0.67. These ones are related to things like a third and 2/3, if you think about fractions, right? The halves and quarters, that's a half, this is a 3/4, and this is a 1/4. When you're dealing with thirds, you turn those into decimal equivalents of 0.33 and 0.67. So 0.33 is going to be somewhere about here, and 0.67 is going to be somewhere about here. Alright, so it's kind of how you would break that up in terms of having thirds or into sections of fourths. So just to kind of have a feel for where things are, so as you play with some probabilities and we start looking at numbers, kind of giving an idea of how certain or likely it's going to happen or how impossible or unlikely it is to happen. So for number 2, it says choose one of the numbers from the previous question. Describe a game in which that number represents your probability of winning. So perhaps you're thinking about something like you're going to do a coin toss and heads wins. That's going to be a probability of 0.50 or 0.5, right? Because that's a 1 out of 2 chance. It's kind of a half right there. Okay. Another one could be a contest where you roll a dice and get a 1 or a 2. If you get a 1 or a 2, that's a 2 out of 6 chance, or about a 1/3, which becomes about 0.33 or so there. Okay, and that's how that kind of works out. So there's some ideas of what you might think about as games you could play and how those probabilities might show up something like there. Alright, so you have a better chance of tossing a coin and getting heads or tails than you do of rolling a 1 or a 2 only on a regular number cube. So now, when you do probabilities over time, in the long run, what you find is that as you go over time long run, the estimations of what a probability should be gets closer to what it actually is. So for example, flipping that coin, yes, we expect it to be about a 50% 50% probability, 1 out of every 2 being heads versus tails. But you might find that sometimes you flip a coin and you get tails, 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 and then you finally get a head and go, oh no, what's going on? If you continue this for the long term, eventually you would get to a point where it's pretty close to being split. We saw 50-50 or 1 out of every 2 times. So that's why we have to look at the long run when we're talking about probability and working with these different experiments, repeating them again and again to get that long-term idea there. Okay, so this is kind of comparing what we call relative frequency versus the actual probability, right? So relative frequency is kind of what's happening in the experiment compared to the probability that we should end up seeing. Again, over the long term, you hope that your relative frequency starts to align with actual probability. So right now, we're going to do an activity with this. Okay, so here we go. Here's your first one. It says list the outcomes in the sample space for rolling a number cube. So if I roll a number cube, sample space, or what are the possibilities that I could actually get if I roll a number cube. So if I roll a number cube, what are the different things I could get? I could come up with a 1, a 2, a 3, a 4, a 5, and a 6. We're good with that. That's my sample space. Those are my outcomes. So what's the probability that May is going to win the game? Now May is going to play a game where she only wins if she rolls a 1 or a 2. So in her case here, there are 2 possibilities where she wins. But that's 2 out of how many? 1, 2, 3, 4, 5, 6 outcomes. So the probability of May winning is 2 out of 6. Or we could reduce that down to 1/3, which as we know as a fraction is approximately, or a decimal, 0.033. That's the probability of her winning the game. Okay, so the chances are she has about 33% chance of actually winning by rolling a 1 or a 2 when she rolls it. So if I rolled it real quick, hey, I got a 1. Hey, that's 100%. If I stop there, sure. But still, no, roll it again. Now we're back to 1 out of 2. Roll it again. Now it's 1 out of 3. That's fitting the pattern. Will it work that way forever? Well, that's what we're going to play with and find out a little bit. If May is given the option to flip a coin, for example, and win if it comes up heads, is that a better option for her? And we've talked about this. Her current option is 1 out of 3, right? That's with the number cube. Let's compare that to flipping a coin. Heads comes up, and that's 1 out of 2. So we're considering which one's the better way, a better chance to get a win, 1/3 or a half. And again, back to your number line, the probability, a 0 is not going to happen, and a 1 is most likely to happen. So the closer you are to 1, the more likely it's going to happen. So 1/3 is about 0.33, and a half is about 0.50. So this one is the greater fraction, the greater decimal, and therefore the greater probability. So it's going to be better to flip a coin because a coin has a better chance of it happening. You get a 1 in 2 chance compared to a 1 in 3 chance there. Alright, so now this next activity is going to take a little bit of work. We're going to be using a number cube, and we're going to roll it, okay, and we're going to record what comes up. Now, May needs to get a 1 or a 2 in order to actually get a win. And we're going to keep track of this here, okay? We're going to roll the die, we're going to write down what the outcome is, and we're going to decide if it's a win or not, and then we're going to say what that fraction of games played that are wins overall. This fraction we'll use as a fraction, and also we'll convert it to a decimal, and I'll use my calculator for that part just to save us some time as we go along. Okay, so first thing we're going to do is we're going to play this game 10 times, and we're going to keep track here what we get. So here we go, our first roll. Remember, she wins if she gets a 1 or a 2. First roll was a 4, so any wins, 0, so it's 0 out of 1, so that's going to be about 0.0, in case you weren't sure how that works out. I'm going to move this over here so I can roll to see a little better. Alright, so we're going to roll it again. This time she gets a 5. So 0 wins. That's 0 out of 2, which is still a 0 win streak. Way to go. Hey, we got a 1. Now 1 is a win, so she has 1 there, which is 1 out of 3, which is 0.33. Roll a fourth time. Got a 5. She's total wins is still 1. She only won 1 time, so now she's 1 win out of 4, which is 0.25. Rolled it again, got a 1. So now she has 2 wins, which means 2 wins total out of 5. 2 out of 5 is actually 40.40. Just want to just happen to know. You could do it this way. 2 divided by 5, get 0.4, so that works too. Let's roll it a 6th time. She got a 5 again. Man, this is a 5 kind of die. Still total is 2, so she's 2 out of 6, which is back to 0.33 again. Roll this again. Now she got a 3. So still just the 2 wins there is all we have. And so we're 2 out of 7. I don't know what 2 out of 7 is, so I'll do 2 divided by 7. And we have, that's equal to 0.285. 8th roll, we get a 2. A 2 is a win, so that gives us 3 wins, which is 3 out of 8 total. I don't know what that is, so I'll do 3 divided by 8. Gives me 0.375. 9th roll is another 5. Boy, pick a 5 for this one, huh? So that's going to be 3 out of 9, and we're back to 0.33 again. And our final roll gives us another 5. I can't believe that. Which is 3 out of 10, which in this case is 0.30. So we've managed to roll this die 10 times. We got 5, 1, 2, 3, 4, 5 times. Seems a little odd. I would think there's probably something maybe wrong with this dice. Anyways, but we got a total of 3 wins out of 10 for the average fraction played in terms of the average probability or average wins was 0.30 for the 10 times there. Now what we want to do is we're going to take these points here and we're going to plot them on the graph on the next page. Okay, so on the first roll, the fraction of games played that are wins, well, the first roll was 0. We had 0 wins. We started at 0, and then we went to, well, we started here and started at 0. For number 2, we had 0 wins, so we're going to plot that point at 0 as well. And number 3, we got a win finally, so we jumped up to 0.33. So at 3, we jump up to 0.33, somewhere about here. On the fourth roll, we didn't win, so we went down to 0.25. So we'll drop this down here to 0.25. And then we went on the fifth roll, we had a win, so we went to 0.40. So we jumped up to here. On the sixth roll, we had no win, so we dropped to 0.33 again. Seventh roll was not a win, so we went to 0.285. So we drop below here. The eighth roll, we got a win, so we went to 0.375. The ninth roll, no win, dropped to 0.33. The 10th roll, no win, dropped to 0.30. Alright, so that's what's happening so far with our first 10 rolls. Okay, we started here, right? We had 0, and then we went up to this point, to there, and then going down and down and up and down and down. Okay, so what appears to be happening with the points on the graph? We'd said before that she has a 2 out of 6 chance of getting a 1 or a 3, or approximately 0.33 is her probability of getting that. Now we think about 0.33 as being a point on this line here, somewhere around there. What we can see, and this is 0.33, what we can see is over time, what's happened is our probability, it did move around a little bit to begin with, but it seems to be bouncing less as we go on, and it seems to be hovering closer and closer to our predicted probability, right? So the more we do it, the more we stay within that or near that green line. The more rolls we have, the less change seems to be happening in our graph. We're not shooting way up here or way down there. Once we got out of the 0 range, we bounced up here, and we never really moved much, right? We're always within 1 or 2 tenths of the green line after that, right? You can almost take a look at it like this. Here is 2 tenths, right? 2 tenths there. Here's 4 tenths here. And all of our points stay within those 2 tenths. It's in that range almost the entire time. So after 10 rolls, what fraction of the total rolls were wins? Well, after 10 rolls, we had 3 out of 10 wins. How close is this fraction to the probability that May will win? Well, in that case, we're saying, well, we thought it'd be 1/3. It wasn't, so we subtract 1/3 minus 3 tenths, and then we're going to look and see what we get. Okay, so to do this here, we have to have a common denominator to make this work, so we'll make this one 10 over 10, so this becomes 10 over 30 minus 3 over 10, which is 3 over 10. Oh my goodness. This will become times 3 over 3, becomes 9 over 30. So we're the difference here of what we expected, what we got, is actually a difference of 1/30, or in our case here, 1 divided by 30, 0.033. 0.033. So how close is the fraction? It's really, really close. So ours just happened to come up pretty close. You might do it in class and get a different number. That's okay. But we expected, to have something pretty close, and we were at 3 tenths. So the difference between 1/3 and 3 tenths is not a whole lot when you do the math on that one there. So we're very, very close to being the predicted value. Now what it wants us to do next is it says to roll the number cube 10 more times. Okay. So let's see where we left off at. We left off with 3 out of 10 is where we left off at. Right? We had 3 wins, 3 out of 10, and that's where we left off at. So let's continue this here. I'm actually going to use a different die because that last one got me lots of 5s. So let's see what happens. We keep on going. Okay, we'll do that 10 more times and see what our result is going to be. So we roll it once. Oh my goodness, another 5. So we just have still 3 wins. So it's 3 out of 11. 3 divided by 11, which is 0.27. Roll it again. We get a 1. Hey, we got a win. That's 4 wins, which is 4 out of 12. Now 4 divided by 12 is, what do you know? It's the 0.33 again. Roll it again. We get a 2. That's a win. That's going to make us go up a little bit, isn't it? So adding to our win column, so we have 5 wins out of 12. 5 divided by 12 is 0.41. We roll it again. Another 1. That's another win. Wow, that's really good for us, but not good for our prediction. So 6 divided by 12 is half, so 0.50. We rolled a 2 this time. So now we're really beating our predicted average, aren't we? So 7 divided by 12, so 0.58. Interesting. Oh man, another 2. I don't know how this is possible, but it is. So 8 over 12, which is going to be, in our case here, 8 divided by 12, 0.66. So we're way over our expectation. I'll roll another one here. Another 2. Oh my goodness. So that's going to be 9 wins, so 9 out of 12, which is going to be 0.75. I'm going to change dice because this is driving me crazy a little bit. Oh my goodness, I don't even know how that's possible. That's 10 wins, so 10 out of 12. This is really going to mess up our idea with this lesson, but that's okay. 0.83. We'll try another one here. We got a 5. What do you know? Shocker there. A 5. Apparently there were no other numbers besides 1s, 2s, and 5s today. So 10 wins there out of 13. 13. Why do I say 13? Oh, I've been changing my number. Sorry. Let me change this here a little bit. I got carried away. I've kept making it 12, but really this should be going up by 1. Oh my goodness! Alright, see, in math you can make mistakes, but you also can use your eraser to fix those things. So here we are. This is 5 out of 13, 6 out of 14, 7 out of 15, 8 out of 16, 9 out of 17, 10 out of 18, and 10 out of 19. Oh my goodness, so sorry. I could rewind and redo it, but I don't have time. So we have, this is 0.38, and then 6 divided by 14 is 0.42, and 7 divided by 15 is 0.46, 8 divided by 16 is 0.50, 9 divided by 17, whoops, 9 divided by 17 is 0.52, 10 divided by 18 is 0.55, 10 divided by 19 is 0.52. Ah, goodness, so sorry. And our last one I rolled, oh, I can't even believe it, another 5, which is 10 out of 20 for 0.50. Okay, so besides the fact that I messed up a little bit in doing my numerator, my denominator, not changing it, sorry about that, had to redo it, we end up with the fraction of total wins that were wins was 10 out of 20. Okay, which is about a half, right? How close is that fraction of probability that maybe we'll win? We expected it to be about 1/3, right? We expected 1/3, and 1/3 is going to be less than a half. So not quite the same, is it? This is 0.33 compared to 0.50. So if you were to subtract those things there, or approximate there, we are about 0.17 off, right? We're too high by about 0.17, which is quite surprising. But again, looking at the rolls we had there, something was a little funny with the die we were using, wasn't it? We had all these 1s and 2s all the way down. We even changed and we got 2s, and we had 5s. Just a really strange situation. Yours might be very, very different. But if I wanted to, take a die somewhere and say, hey, I bet I can get a 1 or a 2, maybe I'd use this one again because it happened a whole lot of times. Very, very strange. But the idea is the more we do this, the more we're going to see that change happen. So it wants you to record this on the graph as well. So let's do that real quick. So at 11, we're at 0.27. So 11 is at 0.27, which is about here. 12 was 0.33, so back to here. Then 13 was 0.38, so moving up to there. And then 14 is 0.42, 15.46, 16.50, 17.55, 18.55. I think I skipped one. That's okay. 0.42, 0.46. Let's see, what did I skip? I don't even know. 14. We'll do another one there. And then 19.52 coming back down, and then landing at finally 50. So in our case here, our graph continued to go up because for whatever reason we kept winning until we started to finally lose. So this is very, very strange. So this is where, if you're doing probabilities, something weird was happening here, wasn't it? And we saw we were winning a lot, and we did not expect that. We expect to be in this range, and so if we play this to 20 more times, I would expect this to drop back down into that range there, potentially. Okay, that's what we're seeing. Very, very unusual. So for each situation, the next one, do you think it's surprising or not in terms of results? You flip a coin once and it lands up heads. Is that surprising? I don't think so. That's not surprising. It's a 50-50 chance, so that's not too surprising. You're probably going to get heads, but you maybe not. You flip the coin twice and it lands up heads both times. Is that super surprising? No, not really, because it could. It could happen twice. There's only two options. Not a big deal. Now, if you flip a coin 100 times and it lands up heads 100 times, that would be surprising, right? That would not be what you would expect. At that point, you're thinking, like the dice I was using, something's probably wrong with this coin, all right? What if you flip the coin 100 times? How many times would you expect the coin to land heads up? Again, there are two choices, right? There's heads, there's tails. It's a 1 out of 2 chance of getting that. So in terms of how much I would expect if I did 100 times, I would expect 50 out of 100 to be heads. That would be my expectation. I would predict the probability to be about 50 out of 100. Now, if it wasn't, that's okay. What are some other results you could have? As long as it's near 50, it's not going to be surprising. Even if I got 40 out of 100, that's going to be okay. Even if I had more, 60 out of 100, that's going to be okay. It's when you start getting numbers like 90 out of 100 that you go, no, that doesn't make sense. Something is wrong. And that's when people that actually run these kind of games and do some prediction on them would say something's wrong if you're able to get it right all the time. Right? So I used to play games with my sisters when I was younger, and boy, they would always roll the right number to win the game. So I thought, something's funny. I wasn't paying close enough attention sometimes, and they were changing the dice. I don't want a 2, I wanted a 6, and it would magically happen. Anyways, let's say you flip the coin 3 times, and it's come up heads once. The cumulative fraction of heads is 1/3. Awesome, that's true. 1 head out of 3, okay? If you flip it one more time, will it come up as heads again to make it match the 2-4 what it should be? Well, the answer is not necessarily. Not necessarily. It may not do that. It still has a 50% chance of being tails, doesn't it? So just because it's come up more tails than heads doesn't mean suddenly the coin's going to say, you know what, let's give the head a chance, right? The coin's not talking to the backside saying, you know, I haven't had enough chimes, let it be my turn now. So you could do it as much as you wanted, but you never know what it's going to stop at and where it's going to land. And it ends up being, in this case, tails or heads. Yay, it wins. Okay. But that doesn't mean it'll happen every single time. So in summary, a probability for an event represents the proportion of time we expect that event to occur. So probability is the proportion of what we expect. For example, the probability of a coin landing its heads after flips is 1/2, which means that if we flip a coin many times, we expect it to land heads up about half the time. That's the expectation. So probability is our expectation of what's going to happen. Does it always work out? No. And we saw that when we did our rolling the die, right? There it is again. Hey, we finally got a different number, a 4, right? And we see it when we flip coins. So even though probability tells us what we should expect if we flip a coin many times, that doesn't mean we're more likely to get heads if we got 3 tails in a row. The chances of getting heads are the same every time you flip a coin, no matter what the outcome was for past flips. So whatever happened before doesn't change what's going to happen probability-wise next. Okay, we're going to pause there, let you work on some homework, and we'll come back and check it together in just a second. All right, homework, Unit 8, Lesson 4. All right, a carnival game has 160 rubber ducks floating in a pool. Way to go. The person playing the game takes out one duck and looks at it. If there's a red mark on the bottom, they get a small prize. If there's a blue mark, they get a large prize. Many ducks do not have a mark. After 50 people have played the game, only 3 of them have won the small prize, which means they were red. And none of them have won the large prize. So there have been no blues after 50. Estimate the number of 160 ducks that you think have red marks, then estimate the ones that have blue marks. Okay, so what do we know? We know that there were 3 out of 50, we're talking about the red ones first, in terms of red ones, 3 out of 50 were picked, okay? So as a probability, this becomes 3 out of 50 is, if you think about it like this, you could think about multiplying by 2, becomes 6 out of 100, which as a probability is 0.06. So 0.06 of the ones that were selected were actually red. So if there are 160 ducks, we take 0.06 and we multiply that by the number of ducks. So what is 6% of 160? And that gives us about 9.6. So in terms of how many ducks there are, we would expect between 9 and 10 red ducks. Because we got about 3 out of 50 were chosen that were red, which is about 6%, and 6% of 160 is between 9 and 10 red ducks. Now, what can we say about the blue ones? Well, for the blue ones, we had 0 out of 50, right? So we know it's less than that. It's less than 1 out of 50. It's less than 1 out of 50. Now, what is 1 out of 50? We multiply by 2 over 2 to show that's 2 out of 100, which as a percentage, or as a probability, is 0.02. Very, very small chance. So 2 out of every 100 might be blue. And we're saying it's less than that amount because we didn't even get one blue one, right? So it's less than that. So let's find out what less than, or what 2% of 160 is going to be. So 0.02 times 160 is 3.2. So how many ducks are going to be blue out of that? Well, less than, we would say less than 3.2. So probably somewhere between, you could say a 1, you could say a 2, you could say a 3, but probably somewhere between 2 and 3 ducks are probably going to be blue if you had to make a guess there based upon what you're seeing. All right, that's one way of thinking about it. Okay, just an idea. So that's that one. So that's more the mathematical way of doing it. Could you do it without all that math? You could probably make some estimations, but the main thing here is if you make an estimation, be ready to explain it. Explain why you did it the way you did. All right, number 2. Lynn wants to know if flipping a quarter really does have a probability of a half of landing on heads up. So she flips it 10 times. It lands heads up 3 times and tails up 7 times. Oh boy. Has she proven that the probability is not 1/2? So she's done heads, 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 and then 1, 2, 3, 4, 5, 6, 7. So by doing that 10 times, does it suddenly change the probability? Explain your reasoning. We would say, no, it does not change the probability, right? It just happens to be that in this experiment, there were more tails. But again, over the long term, what will we see? Long term is going to prove that to be the actual probability. It just takes more time and more flipping of coins. So make sure you explain that there. All right, number 3. It says that a spinner is spun 40 times for a game, and there's a graph to show the fraction of games that are wins under some conditions. So 40 times the spinner is spun, and there's the graph. Estimate the probability of a spin winning this game based on the graph. So to do that, we can kind of see, well, where does this kind of level out at after time? It seems to level out right about here. So if we draw that line straight back, where do we end up at? Well, between 6 and 0.6 and 0.7. So I would say a good probability is somewhere about 0.65. So between 0.6 and 0.7 is a good probability for how the winds are going to work. And again, you can see starts off crazy, bounces around, but eventually starts to settle down like that. I wish that our rolling the die experiment had done the same thing. I could record the whole thing and make it work out better, but that's okay. It's just math and it's just fun. All right, number 4. Which event is more likely? Rolling a standard number cube and getting an even number. Well, 1, 2, 3, 4, 5, 6. There are 1, 2, 3 of those. That's 3 out of 6, which is about a half. Or flipping a coin and having it land heads up, which is a half. Which one's more likely? A half or a half? We would say they are equally as likely. They have the same probability, so the same outcomes could happen either way. And finally, number 5, Noah will select a letter at random from the word flute. Lynn will select a letter at random from the word clarinet. Which person is more likely to pick the letter E? So for flute, F-L-U-T-E, we can see there's one E out of 1, 2, 3, 4, 5 ladder choices. And for clarinet, we see there's 1 out of 1, 2, 3, 4, 5, 6, 7, 8 choices there. So there's a much higher likelihood that the person picking from the flute, which is Noah, is going to find the E before Lynn does. All right, that's it for today. Have a great day, and we'll see you next time.